Hello. Hello, everyone. This is JavaScript Competency Center week, and it means that right now we are starting the whole week of technical talks. This event is really amazing, and I'm super excited to welcome you all here today because today we'll have just the intro section for this particular event, and we will start with our first technical talk. But before that, let me tell you a bit about this series of events. So it's all about bringing together JavaScript developers all around the world so you can share your ideas and your tips and tricks how to build top-notch software in JavaScript. So prepare yourself for a week full of technical stuff and get ready to have your things dirty with the new stuff of the JavaScript world. So let me tell you a bit more about technical talks that we will have during the week. So first of all, will be about design patterns for microservices. So in this talk, Alex will tell you more about design patterns for microservices and will share his ideas and tips and tricks how to build scalable microservices using JavaScript best practices and design patterns. So that's going to be it. Also, the next day we will have a technical talk about how to automate translations with headless CMS. So there, Nazari will tell you all things that he knows about stuff related to CMS. Then the next day we're gonna proceed about tests. So this technical talk will be called "Do We Really Need Writing Tests?" So here we've got like a super trio of technical experts. We've got Ivan, we've got Alexei, and we've got Andrei. So these architects and engineering manager will tell you all this stuff about tests. Then we're going to proceed to the next talk, and it will be all about TypeScript. So in this talk, Stepan will share his thoughts and ideas about how you should work with TypeScript and how you can make your project even better with TypeScript. And last but not least will be a talk about behavior-driven development by Anton. So here Anton will tell you all the stuff that he knows about the proper alignment of developers and business analysts and how to make things better. So that's the stuff that we prepare for you. So I promise you it will be a really good week full of technical talks, and I'm pretty much sure that you're going to enjoy it very much. But before we start with our first talk, let me tell you a bit about the general stuff of these events. So we have comment section. So please don't be shy and put your questions or your notes or your ideas or everything that you want to share with the audience just in the comment section. So that's why you will have a chance to get a prize, because literally after this particular technical talk, we're going to choose the best question, me and Alex. And if you are the lucky one, you'll get this prize. So yeah, get ready and post your question into the comment section. And also, we've got a lot of social networks like Instagram or Telegram account. So yeah, follow us. So let me tell you a bit more about the upcoming talks that we've got so far, which will start approximately in a minute. So in a minute, as I said, you will know more about design patterns for microservices by Alex. So let me tell you a bit about this talk. So if you're a young developer, right, or if you don't have like a lot of experience writing microservices solutions, you might not think about microservices design patterns at all. But at some point in your career, right, you really need to increase your reliability. You really need to improve scalability of your code and literally to do things better. So in this case, you might start thinking about design patterns for microservices. And like in general, I do understand that it's not something new. It's not, like rocket science or some stuff like that. But literally, this is the stuff you have to know. Like, this is the stuff that you have to know, like usual design patterns. So design patterns for microservices is yet another thing that you have really to know if you work a lot with microservices. So, without further ado, I will pass the microphone to Alex. And by the way, Alex is a great developer. He's a triple AWS certified. He's a technical reviewer. He's a mentor. He's a head of UK engineering community, and in general, he's a great guide. So, Alex, back to you. Now the stage is yours, and the audience, please enjoy Design Patterns for Microservices by Alex.
Thank you very much, Pavel, for the great introduction of me and my talk. And colleagues, thank you very much for being here this morning with us today. I suppose you will enjoy our talks. And I have a lot of things to tell to you today. So let's do not waste the time and finally let's start. So, as Pavel said, my name is Alexander Barmin. I'm chief software engineer. I've been to software engineering for more than 12 years, I suppose even more, but I don't remember exactly. And actually, I've dealing with microservices for a long time. And if you go to the Learn portal, you may search for microservices intensive crash course. And if you find it, it will be mine course about microservices. So there is a self-based version. So I hope you will enjoy it. Other than that, at the moment, I'm developing an application for the big European bank, which is built on top of a big collection of microservices. And previously, I also was working with them, so I'm quite familiar with them. And as Pavel said, I'm a head of UK engineering community. Just a few words about the engineering community itself. So we started, the community was started many years ago, but it's active since 2021, and we have already conducted more than 15 events. We have almost 1,000 of subscribers on our community. And other than that, I strongly recommend you to join us because we have weekly links which are published every Monday or every beginning of the weeks. Other than that, we have a community on Yammer and we have memes. So memes are published daily. So join us and you will have good mood every day. Let's move forward. And as ordinary, let me start from from the disclaimer. So, microservices is a complicated topic, and unfortunately, there is no silver bullet. There is no single solution which you can, let's say, learn once and use everywhere. Nevertheless, it means that there are many different options, and it means that as more option you know, as better solution you can propose. So I'm not saying that this is the one single possible way of building microservice. What I'm trying to tell you today is that there are different options, there are different approaches, and the approach you go to use to in your own solution depends on your circumstances. So let's finally start and start with a small introduction into the subject area. Let's imagine that you're building a big new application, or you're migrating your existing big monolithic old-fashioned application to microservices. And this is how you can imagine your monolithic app. It's a one big block. And when you split it into microservice, you can imagine that it will be something like this, four blocks, which are quite similar one to each other. They are, let's say, fancy just because you're building them from scratch. But in reality, you will have something like this. One microservice is bigger. All of them have different responsibilities, relatively different responsibilities. And other than that, more likely they will start talking to each other using REST, using message queues, and well, your solution is became more and more complicated. And next, more likely you will get some clients which will definitely talk to your microservices using, for example, API gateway. And in these scenarios, API gateway is building connections between all your services. Well, you see that picture became more and more messy. And if you keep in mind that we're building microservices for, let's say, for big velocity development, for high scalability, more likely you will have more instances of every service. So as you may see, and as Pavel mentioned at the very beginning, microservices are not so simple as them seems. So you need to follow some patterns and not in order not to fall into the rabbit hole of endless problems. And first of all, first topic I want to cover today is decomposition strategies. This can be applied when you're splitting your microservice big monolithic application into the set of microservices, or for example, you're trying to establish what will be in boundary of every microservice service, even in case if you're building it from scratch. And before we start, I will need to tell a little about what is the service actually. A service is something which has a public API, obviously. And in public API, we ordinarily have two blocks. First of all, it's on top on this slide, it's comment and queries. And this part of API defines operations. And on the bottom line, on the bottom side of this slide, we have event publisher. Why it's important? Because, when service works, it needs to be communicated by third parties. And these third parties may send, let's say, comment or may request some data from the service itself. And in this case, we're using comment and queries public service API. And when service works, it also quite ordinary emits some events. And these events can be used in order, let's say, to react on change in data of your service. So in case if you have a service client, your service client may invoke comment and queries from your service API. And at the same time, it can subscribe to events. And in this case, events are also quite important because, again, we're building microservices for high reliability and for high resiliency. And in case if we need to increase resilience, it means that we are keen on async processing of our data. And event-based communication is key here because if we're making asynchronous calls, they definitely reduce reliability. But in case if we're buffering messages somewhere in the middle, and we will definitely talk about it later, it will increase, let's say, reliability as well. So this is our service. In common, in have service API and events which it emits. So what can we do in order to understand what responsibilities our service should help? And these responsibilities are actually not coming from top of our head. Well, today I want to build service which will process my orders. Responsibilities of the service are defined by your functional requirements. There are functional and non-functional requirements, and non-functional requirements you have already considered, by the way, because you have already chosen microservice architecture. And right now, using this approach, you need to implement your solution. So your functional requirements are starting point for defining what operations you will have in your service. The starting point to defining system operations in your service. For example, this example I will use across all my talk today. We will build a small system which allows us to place and process orders. And as you may see here on the left-hand side, I have a couple of functional requirements saying that as a consumer, I want to place an order so that I can to do something. And in this case, it seems that I need to have a create order operation in my public API of the service. And secondly, as a restaurant, I want to accept an order so that I can do anything else. And in this case, as you may see, I defined a two system operations which represents external requests to my service. Why is it important? It is because, your public API should be as concise as possible in order, let's say, not to be first of all overloaded, and secondly, in order to have enough operations to perform your basic operations. So in this case, your starting point is your functional requirements. But how can you work with it? You're, let's say, defining, collecting all the requirements you have, and you're starting reading them. We haven't started splitting, let's say, big monolith applications into microservices, or for example, um, we haven't started, let's say, building small services which are responsible for every step. Well, keeping in mind that we're building, let's say, distributed application, more likely we will have more than one service, and every service will be responsible for something. And how to define boundaries of the service? We will talk about it in a moment. But the next step is obviously is to define a service-to-service communication or intermediate operations. And again, these intermediate operations can be extracted from your functional requirements. And up to this moment, what we have is a collection of public operations, which can be called externally. And other than that, based on our functional requirements, we can get a collection of intermediate internal operations. But still, it doesn't bring a lot of light for us how exactly we should split our responsibilities between services. And here we have a couple of approaches, by the way. First approach is decomposition by business capabilities. Why is it important? We're building microservices or we're building applications in order to solve some business problems. If we're dealing with orders, more likely we have to deal, we're automating something like let's say a cafe, so that this organization already have some established processes which are working even without automated system. For example, supplier management, accounting, consumer management. And when we take a look into it, we will see that actually inside every capability, inside every business capability, we have some responsibilities. For example, management of careers or management of information about restaurants. And when we look into it, we may notice that, well, it seems that some operations, like here on the top, can be converted to separate service because, let's say, they are quite complicated. Let's say career management, it is not only about managing a collection of careers, it's also managing about their current, let's say, occupation, their current position, and so on. And also inside our business, we can have a small capability which can be converted to one single service. Or, for example, we can have multiple capabilities which can be converted to the single service. Why is it important? It's because, again, we are not building microservices in a vacuum. We are building them keeping in mind our business. So that we're looking into what we have, what our organization does, and next, splitting these responsibilities into service. I'd like to mention that we're not doing it once and forever. And definitely at some point in time in future, or we may notice that some services do not have enough responsibilities, or some service has a lot of responsibilities. And microservice design allows us to split and separate and join services easily. This is one approach. And second approach, which is also a good way of doing it, is domain-driven design. In domain-driven design, our subject area is split into subdomains. For example, like here, we can have a separate subdomain which is responsible for accounting, separate subdomain which is responsible for delivery management, and so on. So way of splitting your application into microservice depends on what your business is doing actually. And in case if you, for example, dealing with I don't know, with customers, it seems that more likely you will have a service which is responsible for dealing with customers. In case if you're dealing some accounting for different areas, more likely you will have a separate service which is dealing with accounting, or maybe set of specialized services which are responsible for it. When you build a collection of services, obviously services have to talk to each other in order to build some, let's say, in order to process requests which are coming to them. And here, obviously, we have inter-process communication. And actually, there are many different ways, but in common too, how we can do that. And obviously, it is sync and async communication. In case if we're doing a sync communication, what we ordinarily do, we're just sending requests and receiving a response back. And our response also can be paired with some events which are also emitted simultaneously. And in this case, what we can notice is that communication is happening at the same time. So both services should be available at the same time, which again, quite good for some circumstances. For example, you want to build a responsive UI, and at the same time, maybe not good for another circumstances. For example, you have a quite high load, and in case if your load exceeding amount of resources you have, you may have outages. So please keep in mind, so SIM communication is not always fine. So that there are different options how we can make it more reliable. We can synchronously send request and next wait for a response in a separate queue. So you have definitely seen this, let's say, pattern of behavior when you're, let's say, clicking a button and getting a message. Okay, your message is added to the queue. You will get this. You will get a response, let's say, by SMS or by email or by something. Well, it's really easy to imagine it, but it's quite complicated to implement it. And the main complication here is that you need need to understand what in the response queue corresponds to the request. And here we have another quite useful design pattern, which is called correlation ID. So every request has a correlation ID, which is let's say a some value which uniquely identifies it. And when you're getting a response in the response queue, you may know what exact for what exact request you're getting this response. I need to tell a little about this correlation ID. So obviously it looks like it would be nice to add a separate field in your request saying this is my correlation ID, which is unique identifier. And next in the response messages, you will get this correlation ID somewhere. Yes, this is an option, but also if you take a look into your subject area, more likely you will notice that majority of your entities already have these unique identifiers so that you can use them as correlation ID as well. For example, you're creating an applicant, creating a new customer, and this new customer will have its own ID. So this ID also can play a role of correlation ID. Other than that, there is a different approach, which is called notification. And in case of notification, you will definitely just sending a message and not expecting any response back. And you also may notice this behavior somewhere. For example, you're ticking a box saying, I'm putting a like to this message or to this talk, by the way. Don't hesitate to put likes to this talk. And your UI just saying that, oh, your like is added, but you're not getting any response back. Okay, and by the way, please don't forget to put your comments and questions to the chat. Moving forward, it's quite ordinary. We have a situation when one client can send requests to multiple services, and it is not because we want multiple services to process the request, but we know that our requests might be processed any of the instance in the backend, in the background. And in this case, what we can do, we can, let's say, put this request into the queue. And next, this request will be captured by any instance which is able to process it. And for example, if you know Kafka is working in a quite similar way, you're just putting a message to your topic, and next this message can be captured by any consumer. Well, but again, in this case, we're just adding a message and not getting the response back. We can make this approach even more complicated and not only send requests asynchronously, but also expect the response asynchronously. And again, the main point here is do not forget about your correlation ID, because this correlation ID will allow you to understand what what response corresponds to which request. So in this case, this is what you may have. You're sending a request, this request goes to a particular queue, and next messages are taken from this queue, and the response is obviously added back to the queue. Well, you may say that actually you have never seen this way of communicating. Well, maybe yes, maybe not. But for example, if you take a look into the AWS or API gateway in AWS, what it allows us to do, it allows to establish a buffer between your services and API gateway. And this is exact the same design pattern when your requests are not sent to, let's say, to your consumers immediately, but first of all they are buffered. And other than that, I suppose AWS is, let's say, a good example of a solution which is built on top of asynchronous communication. They have a lot of talks saying that our world is actually asynchronous, and this is, let's say, their philosophy. And by designing microservices, you should definitely keep it in mind that actually we built microservices in order to make processing asynchronous because it's a bit more reliable. Moving forward, need to do an intermediate summary. Obviously, in case if we have a synchronous communication, it's simple and well known because we're just sending a request and do not have to wait for the response. And obviously, it does not require any intermediate broker because it is also because we're just sending a request, receiving a response. We don't need to buffer our messages anywhere. That's fine. But nevertheless, it also has some drawbacks because, first of all, it reduces availability. In case if we need free services to process the request, even if all of them are available 99% of time, it means that reliability is definitely less. Is definitely less. And other than that, we're creating coupling between our services in this scenario because services should know I'm sending a request to another service, and it seems I need to know at least URL or IP address of the service which will process my request. In case of async communication, it's quite fine because it also has some benefits because it's not blocking. It's really good at scaling. In case if you have a buffer in between your services, you can use this buffer to scale your consumers. And in this case, requests are not targeted to a specific service because your client is communicating with broker only. But nevertheless, there are some significant drawbacks you also should be aware of. First of all, it's exception handling because well, it's quite complicated to understand why your message was not processed. It is because of message broker is down, or because your data is not correct, or for example, consumer is not available. So I think communication creates complexities here. And another drawback which you should be able to aware of is that response time can be unpredictable. Well, it's quite obvious because our messages are buffered in the middle and next they're captured for processing. And for example, in case if our consumer is not available for some time, our producer may not know that. So by designing a synchronous system, you should keep it in mind. And obviously, it's not really easy to make this communication reliable because you cannot just send a request from one service to another. Well, it would be nice to do it, let's say, in better way in order to simplify development, testing, and maintenance. Let's start with synchronous communication or synchronous remote procedure invocation. Literally, it means that we're calling business logic from one service is calling something in another service. And you may have a quite, let's say, you may have a quite a good intention to call service A from service B directly. For example, by creating, I don't know, an Axios client and sending a REST call to it. But it would be nice to follow a bit different approach. And instead of calling one service from another directly, it would be nice to have a remote procedure invocation proxy in the middle, which will definitely hide complexity of service to service communication. Why it is important? Because this proxy will not only simplify your life and testing, but also will be responsible for some cross-cutting functionality, like let's say service discovery, retries, exception handling, and so on. And you will be able to reuse it across your services. On the other side, again, your API proxy is calling another proxy, which is calling business logic of your another service of your consumer. And again, this is a quite well-known design pattern, which is called, let's say, separation of concerns. And in this case, services are not communicating directly. They are communicating via some intermediate, not a broker in this scenario, but via some proxy. And another good benefit of using it is because it significantly simplifies testing because you can mock communication with third-party service. Services do not know anymore that actually they need to, let's say, to send requests synchronously, need to do some service discovery, exception handling, and so on. You can mock with proxy and test your business logic in isolation. As I mentioned multiple times before, synchronous communication is not really reliable. So that's it would be nice to keep in mind that when you, for example, are sending a request, this request might not be processed. And in this scenario, it would be nice to have a fallback response. This is another good design pattern to keep in mind. Nevertheless, it is not applicable in all the scenarios, but for example, in some scenarios it does. For example, you're building, let's say, a UI for application which gives some recommendations for the consumers. And in case if you can, let's say, do some personalized recommendation by your service, that's fine. But in case of service of personalized recommendations not available, you can do some return some cache data. Uh, so as I mentioned at the very beginning, I'm not giving you exact examples. I'm just giving you building blocks. Another good design patterns to be aware of is service discovery. Idea here is quite simple, but at the same it's quite complicated to implement because different approaches exist. And I can explain it simply in the following way. Let's assume you have a client which calls my order service, and this order service is created and destroyed dynamically. For example, based on the workload I'm monitoring, CPU usage of my service, and in case if it's going uh, uh, ahead of some threshold, I'm creating new instances. If I don't have enough workload, I'm reducing instances in order not to waste money. And in this case, my services are created automatically, and at the same time, we're getting dynamically assigned IP addresses. And it seems that my client should be able to somehow distribute requests and queries across these instances. And here we have two approaches. Obviously, client can do it on its own, and this is called application level service discovery. It works in the following way. We have client, and inside the client, we have service discovery library. And other than that, we need to maintain service discovery as a separate service on our own. And this service discovery service will definitely publish at least two API. Written with mistake registration API and query API. And this, in case if order service rises up, it also should have a service discovery library. It receives an IP address from the dynamic, let's say from some source. And next, what it needs to do is to register itself in the service discovery. This part of pattern is called self-registration. In this case, service discovery is, let's say, is receiving some information about service itself. And the new instance rises up, it also registers itself in the service discovery. And in this scenario, service discovery is also responsible for checking which instances of my service are available, which of them are alive, and which of them can accept traffic. So I have service discovery like a table which has a correspondence between service name and their instances. And next, when client need to make a request to one of instances, it is making first a request to the query API asking, hey, dear service discovery service, please tell me what instances of the order service is available. And next, service discovery or service registry returns a collection of IP addresses. And next, my service discovery library needs to make a decision which exact service to call. And as you may see, we have a lot of logic written in the service, in every service, because every service needs to do, let's say, self-registration, need to make a query, need to do a decision of what exact service to call. On the one hand, it sounds like it's a great flexibility, but on the other hand, so we need to maintain this functionality in every service. And complexity here is that if we have services written in different programming language, some of them are written in JavaScript, another is written in, for example, in Ruby, in Scala, in Python. All of them should have these two components for registration and for querying the service registry. In contrast, we have an approach when we don't need to do anything on our side, and everything is maintained by our deployment platform. But honestly, it works similarly. When service rises up, it also gets an IP address, and our platform, like Docker Swarm or Kubernetes, uses a component which is called registrar. And this registrar is maintaining service registry for us. So it knows what services are available and where they are. And in case if our client want to make a call, it needs to use service DNS name, and this service DNS name will be next by resolved to a virtual IP addresses by router platform. In this case, we're doing service side discovery or platform side discovery. We're not doing it in our application. And next, we're obviously making a call. So something like this. Uh, what's the benefit of this approach? Obviously, it doesn't require us to do anything, right? Right. Um, because let's say everything is managed by platform, but on the other hand, it doesn't allow us to be flexible, because in this scenario, we're limited to capabilities of the platform. For example, if we want to select a service which is, let's say, is responding quicker than other, we can send more requests to it. In case if we have a service which has less work or created recently, we can do it. We can select it by using our service discovery library. But in case if we're managing this discovery by deployment platform, we may not have this capability. So let's do a short summary here. Yes, application level service discovery is platform agnostic because it can be started anywhere. But at the same time, we need to have a service library for every framework of every programming platform we use, and we need to maintain service discovery instance or service on our own, and it can create a bottleneck, by the way, because if this service is not available, well, nothing is working. At the same time, we have platform provided service discovery, which is obviously handled by platform, and we don't need to do anything. And in this case, we're getting couple of interesting drawbacks. We are limited only to platform capabilities, and we're getting vendor lock. So I have a couple of questions, and let me answer at least one of them. There is a question: what is the best way of microservices to communicate with each other? And as ordinary, there is no good answer. So because after of this question is asking whether it's HTTP, gRPC, or maybe it is RSocket, and it depends on what you're building. In case if you're building, let's say, a simple service, let's say a simple application, and you don't really care about, if you don't have a, let's say, worldwide traffic, which is, let's say, overwhelming your system, and you don't want to, let's say, um, maintain a complicated schema, you may use HTTP because it's convenient. It's really easy to use it. You can capture request and debug it in the middle. But in case if you have a heavy load and you don't want, let's say, um, to use less verbose protocol, obviously, yes, you're moving from HTTP to gRPC because it is more rich protocol. It's a binary protocol, which is providing, let's say, great versioning capabilities. And in case if you're building a reactive services and want to have a back pressure capability, maybe you should think about our sockets. So there is, as I mentioned at the very beginning, there is no silver bullet, and you need to keep in mind what exactly you're building. And my personal recommendation here is that do not overcomplicate from the very beginning, because design of a main idea of microservices is that you're defining public API, and next you can migrate from one technology to another smoothly. For example, you have a couple of services which are talking to each other using HTTP, and what you can do is, for example, build another instance of the same service which is talking using gRPC and smoothly migrate from one way of communication to another. And for example, in this case, or for example, you may want to rewrite it from old-fashioned Java with a significant with heavy footprint to tiny JavaScript application, because why not? And microservices allow you to do that. But what you should keep in mind is that this decision should be done wisely. Okay, I still have a lot of topics to tell you. Hope I answered your question. So let's move forward and let me tell you a little about reliable async communication. Because what I told previously is that, well, it seems that it's better to use async communication in favor of async communication. But actually, it is not really easy to build async communication properly as well. And here, first of all, idea is similar. Instead of just sending a message directly from your business logic, it would be nice to have a message sender. Let's message sender component, which will be called from sending port of your business logic. Next, it also can add some correlation ID to your code, to your message. And next, it will send message to some messaging infrastructure. And messaging infrastructure, in this case, it can be, let's say, kind of a broker. I'm not talking about broker because obviously there are different ways, not only broker-based communication. And on the other hand, on the consumer service, what you may have is a message handler, which will be responsible for capturing messages independently from your business logic. And in this scenario, message handler will call your business logic. Good. Let's move forward. So, and key key points here. Again, we're not calling a message sending and handling directly from the business logic. We have something in the middle. Moving forward, and actually, we have two ways of communicating between services. It can be brokerless and broker-based, or and it sounds like we are quite often use approach which is on the right hand side, but still we have a lot of applications which are using brokerless architecture, and you may say that you have never seen it. So obviously what we have on the right hand side of this picture is Kafka or RabbitMQ, or for example AWS SQS in the middle, or AWS MQ or Kinesis, something like this. But also we have a brokerless architecture, and the brokerless architecture is quite widespread in some data processing application. So you don't always need to have a broker, and as a buffer, what you can use is a simple folder on your file system. And in this case, one application is just writing to a particular folder, for example, a collection of XML documents, and another application is just reading this folder and processing messages from it. It is quite widespread in old-fashioned enterprise applications because it is quite reliable. We don't need to have intermediate component. But in this case, there is a significant drawback that we cannot push messages, which just can pull them. For example, service A put some messages into for files into the folder, and service B just pulls this folder instead of being pushed by getting a message. And so that obviously all of them have different benefits and drawbacks. So broker-based is simple. It allows us to build a loosely coupled application. They don't know about each other. We have message buffering and more likely message persistence. And still, in case if our Kafka died, our application, our solution may not work, and it introduced additional operational complexity because we need to be responsible for managing this component which is in the middle. And what we have on the other side is brokerless, because besides using let's say a folder, what else we can use is ZeroMQ, for example. This is a similar tool as a message broker, but it does not buffer messages. On the one hand, it sounds like we increasing the latency because we're sending messages directly, but still or maybe we don't need to manage a separate component, but still our application became familiar of each other, which is not really good, and we're reducing availability and increasing application complexity because applications became known to each other. And there is a quite good comment, I can see it in my chat, that sophisticated message brokers like Azure Service Bus or Kafka and service and publisher subscribe pattern simplify inter-service communication and eliminates use of service discovery. And this is actually true. This is actually true because, well, migration to clouds simplifies our life on the one hand, because you don't have to manage your message broker, you don't have to manage your API gateways, even service discovery is available out of the box in cloud, but at the same time you're getting a vendor lock. And there is another quite interesting point. I'd like to mention that, well, microservices is not a silver bullet, or let's say distributed applications is not a service bullet. Or at the same time, cloud services are not silver bullet, because if you have seen recently, Amazon Prime Video migrated back from microservices to monolith, because they spent a lot of resources on service to service communication. So on the one hand, yes, cloud services and sophisticated message broker allows us to solve a lot of problems, but at the same time, we should be aware of additional, let's say, complexity that they bring, and we should be aware of additional, let's say, overhead which they bring to us. Moving forward, handling of duplicated messages is actually a quite complicated topic, and because we have a message bus, we're keeping in mind that communication might not be reliable, so that we should have a way to handle duplicated messages. And the easiest way to do it is to store all the messages we have already processed in a separate table in the database, or separate collection if you're using non-relational database. And it would be nice to update both the collection or table simultaneously, like you're updating your business table and you're updating a collection of processed messages. In this case, if you're getting duplicated message again, your insert will fail due to the fact that message is duplicated. Another approach here is that you're checking that message with a given correlation ID or given identifier has not been processed yet by searching through the processed messages table. So you may say that actually it is not happening, but my practice and experience says that it is happening regularly, that same messages are delivered more than once. Because, even sophisticated message broker has some limitations, saying that messages have some guarantees, and more often this guarantee is saying that message is delivered at least once, so keep it in mind. Transactional messaging. You don't need to not only receive message once, but also to make sure that your message is sent successfully. And in this case, there is a different design patterns, which is called outbox table or outbox. And what it allows us to do is to store our outgoing messages temporarily in the outbox table. And as soon as, let's say, some business transaction is executed, instead of sending message directly, we're saving it to the outbox table. And next we have a message relay, which polls table for new records, or for example, watches this table, or for example, it may listen to a particular database trigger. And next this message relay is actually sending message to the message broker. So we know how to send and receive messages reliably, but what can we do in order to make our application more reliable and eliminate sync communication? So obviously, a way of doing that are quite simple. Instead of sending requests directly, what we're doing, we're putting queues between our services, and next we're putting another queue which will save the response. This is quite simple and good way of eliminating of synchronous communication. But in this scenario, we're falling into the pitfall when data might be distributed across services. And in this case, we would need to sync data somehow. And here we have a couple of options. Obviously, first option is that we can listen to event and update data, or maybe, let's say, as soon as asynchronous request is received, asynchronous message is received, we can, let's say, send another call to retrieve all the necessary data. But also, actually, there is a bit different design pattern, which is called data replication. So we can do data replication directly, or we can use some database, or maybe not database, but um, or we can use messages which are emitted by these services in order to keep data in sync. So what we have in this situation, we have order service which is calling consumer and restaurant service, and both of these services has their own tables with data. And in some scenarios, order service, what it might do, it may keep a copy of data in its own local database. And in this scenario, when it's necessary to process, for example, a simple order, instead of just sending requests to the services, this order service may use data which is cached here. Well, again, you may say that it is not convenient, but let's imagine a bit different use case. For example, order service is performing some workflow, and the workflow consists of many steps, and every step is obviously independent. And speaking about cloud, it may be Lambda, for example, and uh, or maybe you're utilizing some state machine, and state machine is calling your action independently one from each other, from another, and is instead of just making calls every time to retrieve information about consumer and restaurants, what you may do, you may cache some data temporarily. This is also a good way of doing that. So, what about time? We have not very much time left, so let me move forward. Next important topic is distributed queries. In case if we have a monolithic application, this monolithic application is definitely dealing with one big database which is aware of everything, and we can send the request, and this request will be successfully processed by it. But in case of microservice architecture, it's complicated because our data is distributed across the services, and in this case, the easiest way to do it and more obvious is to use API Composer, this design pattern. So we're sending request to API Composer, and next it splits request into other services. Simple, simple, but it doesn't allow us to solve for more complicated scenario when we need to retrieve not only data by ID, but do some queries, for example, pagination. And in this case, in case if our consumer service is supporting it, that's fine. But in case if our data provider does not have filtering capabilities, we have to retrieve all the data we have. It can be million of records, and do filtering on the API Composer side, which is awful. And to solve this problem, we have a bit different approach, which is called command query and request segregation. Idea is simple. By default, our applications are built in layers. This is what we ordinarily do, and the layer which responds, receives all the requests is ordinarily called front controller, and it may use, which mean it can execute CRUD operation, read, update, delete, using our complicated domain model and send request to database. And in case if we need to do a list operations, what we ordinarily do is write a simple converter, which allows us to convert, let's say, query parameters into SQL in order to do filtering, pagination, and so on. And again, we're using same database for everything. Uh, it works gracefully when we have monolithic application because everything in one place. But in case if we have distributed application, it might not work. So here we have a securest pattern, which will definitely help us to solve this problem. And idea here is the following: instead of having one database, we're having two databases, and one is responsible for process of, let's say, the command-like queries, command-like requests, and second database is responsible for processing queries. So let's wrap up this part and take and do an intermediate summary. And unfortunately, we're quite limited in time, so I will just briefly explain, let's say, show what else I wanted to tell you, and next answer your questions. So simplest way of doing that, of queries, it's API Composer. Obviously, it's simple and intuitive, but it introduces additional overhead, reduces availability, and doesn't allow us to deal with transactions. We may lose some transactional data. CQRS, on the other hand, when we're separating our queries from commands, it allows us to have a better separation of concerns. We can have more efficient queries because, let's say, Elastic is much better at queries than Postgres, for example, but still it has significant drawbacks because we're introducing additional database into our application and we may have a replication lag. So what else I wanted to tell you today is a little about external API patterns. So about API gateway, which lives in the middle between our services and outer world, because we need to hide complexity of our solution, and API gateway is something which allows us to do that. Our API gateway might be definitely layered. For different clients, we may have different API gateways, and this approach is called backend for frontend. And my complication with backend for frontend is who will build it. And here we have different, let's say, organizational patterns. When one team is building, let's say, common layer, and another team is building clients for specific API for specific clients. Another important topic to highlight is how to make our services production ready. Obviously, here we have multiple problems. First of all, is how to get configuration, because when we deploy our services, we are, let's say, can be scaled, when can be deployed in different environments. So that we need to have a way to retrieve configuration for them. And obviously, there are two approaches. First of all, we can push configuration, for example, using environment variables, which is strongly recommended. And another approach is that we can push only minimum amount of parameters, which allows us our service to communicate configuration service, which will and next retrieve all other parts of configuration, which is also good. Another, and I suppose this is the most important bit, is you need to make your service observable. What does it mean? It means that your service should report on its state, whether it's healthy, whether it's sending all the logs to the proper state, whether it's publishing metrics. All these should be available somewhere. The reason is because you have multiple services and you cannot, let's say, capture one single request and trace it from end to end without additional application, without additional capabilities. So observability is number one, which should be kept in mind. This is why microservices are so complicated. And actually, that's it. To make a common summary, I'd like to say that it's hard to build a distributed application, obviously, because you need to combine multiple, you need to solve for multiple concerns. You need to properly split it into parts. You need to establish reliable communication. You need to split data. You need to ensure observability. And I'm saying it again, there is no silver bullet. But the more alternatives you know, then better. The more let's say, cubicles you have in mind, the then better solution you can come up with. Finally, that's it. Thank you. Definitely, there are some questions in the chat, and I suppose we have some time to answer them, aren't we?
Yeah, for sure. For sure, we've got some time. Right. So let me switch to our questions. Uh, let's see what we got. So, do you? Yeah. So, what do you think about the cell-based architecture? Like in general,
To be
your thoughts about it.
To be honest, I have never heard about it because it seems this is something new and something which emerged recently. So if you can share some links about it, I can learn it. But honestly, I have never heard about it yet. Let me
Mhm.
Google.
Okay.
Uh, yeah, this is something new.
All right, Alex. Uh, let's move on. And we've got another question. It's about best ways or practices for certain microservices pattern regarding error handling. So,
Oh,
what
that
about?
complicated topic. So So let me briefly answer it in two aspects. So first of all, if you have a service, as it was on my previous slide, on my last slide, the most complicated, let's say, characteristic of a service uh, is its observability. So exception handling in a particular service should be as simple as possible, and it should provide as much information as you have, because you're posting your message, your error, let's say, trace to the system out, and next the system out is captured by some log collector, and next you see these logs in, let's say, in your Kibana, or for example in CloudWatch, and next you're getting notification about your error. So first of all, services should report about error clearly. Second important thing is that it would be nice to add trace information. Let's say for every request you're receiving, you're including information about request ID. This is called traceability. And this will definitely allow you to see what exact request failed. For example, if you're using a tool like Dynatrace or Datadog, which is collecting information about traces, this will definitely help you. If we're talking about exception and error handling in distributed application as a whole, there is a, for example, you're doing some orchestration. Let's say you have a collection of services which are storing data and you have an orchestrator on top. There is another design pattern which is called Saga, which allows you to, let's say, to do a sequential invocation of your subsequent services. And in case if services are not responding in an expected way, you're, let's say, doing some compensation transactions, you're doing compensation calls in order to roll back data if necessary or modify data somehow. So roughly speaking, as ordinary, it depends. But first of all, service should report as much as they can. And in case if you're doing orchestration, so don't forget about Saga pattern.
Okay, okay, I see. Well, not a question per se, but just a note. Let me voice it out. So Emmanuel actually raised that. So with respect to sometimes broker will break your business logic because of its async, you can use event sourcing pattern to perform synchronous calls queries in async broker-based architecture. So this is a note from Emmanuel. So could you comment on that? Well
Sometimes
then.
broker will break your business logic because it's uh, well, uh, yeah, I suppose it's fair point. Um, I suppose it's fair point, and well, even even communication between services which are using, let's say, broker in the middle also can be, let's say, be blocked. And I also have seen examples of it. When we're sending requests via some message queue, we're also blocking a caller, a calling service or calling thread until we receive the response in a subsequent queue. So that's a fair point. We also can use it. So thank you very much for pointing it out here.
All right, cool. Yet another question from YouTube. So how do you handle cross-cutting concerns such as distributed logging and centralized monitoring in large-scale microservices system?
Oh, that's complicated question. Thank you very much for raising it up, because, well, so short answer is that we create, at least in the solution we're building right now, what we've done is first of all we built a basic Docker image which already has some, let's say, configuration for almost everything. For example, it has configuration for log collecting, which has configuration for which has some tools for instrumentation in order to do, let's say, tracing easily. And second, we built a collection of libraries, common libraries, which is reused across all our services. And what I want to highlight is that it's much more convenient to put all this cross-cutting concern into some basic Docker image rather than supporting collection of libraries. But it's not always possible. Uh, this is what we've done. Thank you. It's a good question, by the way.
All right, all right. Uh, so we've got like literally a lot of questions left, though we are out of time. So I assume that we might use the following pattern then. Uh, You, Alex, will answer the questions later on, right, in the offline mode, and we'll pick the best question of the session, and we will share the prize to this person. How does it sound for you?
That sounds good to me. Thank you very much.
All right, cool. So, so basically, that's it, everyone. Thank you very much for joining this talk about microservices. And before we literally wrap off this session, let me tell you just a few notes from my side. So first of all, big thank you to our fantastic speaker, Alex. You did a great job, really. You've shared your expertise, you've shared best practices. Well done, mate. Well done. Good stuff. So see you next time. Then to you guys, to the audience of this particular technical talk, please subscribe to our YouTube channel, click like button. What else? Turn on notifications. Follow us on Instagram. Well, you know what to do. So just get ready because we've got a lot of updates that we are happy to share with you. So literally, just follow us everywhere. Link will be provided. So the best question will be selected by Alex, and we will provide you the decision. And what else? What's left? Yeah, basically that's it about this particular talk. But I do want to give you just a spoiler alert about the next one because tomorrow we'll have another great technical talk. Uh, and it's going to be about the automation of the translation with headless CMS. So can we have like a picture or something like that about it? Well, it was today, and tomorrow we'll have the CMS. Right. So the talk will be called How to Automate Translations with Headless CMS. So basically, it will be all about how to manage translation process using headless CMS and automation tools. So it's all about working smarter, not harder. And Nazari will do his best to share things with you, and he will enrich your experience and your theory, and hopefully your translation automation will be improved. That's it. Thank you very much. And thank you for being part of this incredible technical event. See you next time. See you tomorrow.